what if computers could, learn and adapt, not just follow instructions, but actually think a bit more like, well, like a brain?
It sounds almost like science fiction, doesn't it?
Totally. Imagine devices that sort of evolve with you, understand context, make predictions, maybe without being plugged in all the time.
Yeah, that's the dream.
Well, welcome to the deep dive. Today, we're going to try and peel back the layers on something called neuromorphic computing.
And it's really not just about, faster
Mhm.
chips. It's deeper than that.
Exactly. It's about fundamentally rethinking how computers work, drawing inspiration from, honestly, the most complex thing we know, the human brain. So our mission for this deep dive is, first, to get a handle on what neuromorphic computing actually is, then explore its potential, which seems, frankly, disruptive,
Definitely.
and then, importantly, we'll zoom right into the hardware, the actual tech, the materials, the devices that are making this brain-inspired future possible.
We'll look at the pros, the cons, the challenges,
Yeah.
because getting the materials right is, well, it's key.
It really is. It's a journey from biology to silicon. Should be fascinating.
Absolutely. And, neuromorphic computing, it's not just a buzzword anymore. It's a whole new way of thinking about computation.
Okay.
At its core, it's an approach inspired directly by how the brain is structured and how it functions. So a neuromorphic computer, or maybe just a chip, uses physical artificial neurons to do the math, basically.
Artificial neurons.
Wow. Yeah, and it pulls together so many fields. Biology, obviously, but also physics, math, computer science, electronic engineering. They all have a part to play.
Okay, so let's unpack brain-inspired. We're not talking about, like, building a perfect copy of a human brain in silicon, are we? That sounds complicated.
Yeah, definitely not aiming for an exact replica, at least not yet. The idea is more about extracting the principles, the structures, the ways it operates that make the brain so efficient and powerful, and then using those for practical computing.
Got it. So borrowing the good ideas without getting bogged down in all the biological messiness.
Precisely. And a core idea here is that computation is really distributed. It happens across loads of small computing elements, these artificial neurons, all connected. Kind of like our own neurons.
Instead of one big central processor doing all the heavy lifting?
Exactly. You have maybe millions or even billions of simpler processors working in parallel.
That makes a lot of sense, especially when you think about efficiency. So how does this brain-inspired approach stack up against, well, normal computers, the ones based on the von Neumann architecture?
Yeah, the classic setup.
Where you have the processor here and the memory over there, and they're always shouting data back and forth. That seems like a bottleneck.
It is a huge bottleneck.
Yeah.
And that's where neuromorphic systems have some big advantages.
Mm.
First off, you nailed it, the memory wall.
Right.
Traditional systems constantly move data between the CPU and memory. Neuromorphic systems, they couple memory and processing much more tightly. Sometimes they're right next to each other, or even combined in the same component. So you avoid all that costly data shuffling. It saves time, and crucially, it saves a massive amount of energy. Think about cooking, but having to run to another building for every ingredient. That's kind of the von Neumann way.
Yeah, that's a great analogy. The energy savings alone sound huge. So data isn't constantly moving. What else is different? How do they actually process information?
Well, second, they often use event-driven processing. So instead of constantly processing everything all the time, they react to specific spikes or events.
Spikes. Like brain signal?
Kind of, yeah. Information is encoded in the timing of these sparse events. It means the system only activates parts of itself, only uses power when something relevant actually happens.
So much more efficient again, like getting only the news headlines you care about when they break.
Exactly that. It cuts down waste significantly.
Okay. And what about learning? We hear about AI training needing huge amounts of power. Is neuromorphic different there too?
That's another key point, yes. These systems often support dynamic local learning. Traditional deep learning uses this thing called backpropagation, sending error signals way back through the network layers. It works, but it's very energy intensive.
Right.
Neuromorphic systems can often adjust connections locally, right where the learning needs to happen. It's much more efficient, allows for real-time adaptation using far less power.
So they're almost built to adapt on the fly. And I read they also do predictive learning. What does that mean practically?
Yeah, that's another brain-like feature. Our brains constantly predict what's coming next, what we'll see, hear, feel. It helps us make sense of the world efficiently. Neuromorphic chips try to mimic that predictive ability. And they also use what's called multi-timescale dynamics, meaning they can handle information happening at different speeds simultaneously, adapting to various inputs, just like we do when interacting with the real, unpredictable world.
This is all sounding like it's really coming together. I've heard people talk about an AlexNet moment for neuromorphic. For listeners, AlexNet was this huge breakthrough point for deep learning driven by GPUs. Is neuromorphic at a similar point?
I think that's a fair comparison, yeah.
Yeah.
The field feels like it's right at that kind of critical juncture.
Yeah.
We're seeing prototype systems moving into the early commercial market pretty rapidly now.
Really?
Yeah, the market for the chips themselves is projected to hit something like $550 million US by 2026. Now, that might sound small compared to the overall chip market,
Sure.
but the growth rate is what's key. It signals a potential shift, much like GPUs did for AI back then. Neuromorphic seems poised for a similar kind of impact, especially because it's so versatile.
Versatile. How so? You mean it's not just for one specific thing?
Exactly. Often computing advances focus either on massive supercomputers or tiny embedded devices. Neuromorphic has the potential to be disruptive in both. You can see it in huge data centers needing better energy efficiency, and in tiny, always-on sensors, maybe in your phone or wearables, doing smart local processing. It could span the whole range.
Wow, okay. That's a big promise.
Yeah.
So to make all this happen, it really comes down to the hardware, right?
Yeah.
The materials, the devices that actually mimic those neurons and synapses. This is where the science gets really specific.
This is absolutely fundamental. To get those neuron-like and synapse-like behaviors, we need new kinds of devices, new memory technologies, and efficient memory is just critical for learning, storing, retrieving information in these brain-like ways.
So what are we looking for? What makes a memory technology good enough for neuromorphic? They must have some pretty demanding requirements.
Oh, extremely demanding. You need incredibly low energy use. We're talking femtojoules per bit, which is almost nothing.
Femtojoules, okay.
You need low latency, super fast reactions,
Okay.
operating voltages under 1 volt, and critically high endurance. They need to be switchable potentially trillions, maybe quadrillions of times without wearing out. Plus, good data retention, scalability down below 10 nanometers, and this is crucial, they have to be integrable with existing CMOS processes, the standard way we make chips today.
That is a serious wish list.
Yeah.
So who are the contenders? What technologies are trying to meet these specs? Let's maybe start with phase change memory, PCM.
PCM is a great starting point. The basic idea is to mimic synaptic plasticity, how connections in the brain strengthen or weaken. It does this by switching a material between two states, amorphous, which is kind of glassy and disordered, and crystalline, which is more ordered.
How does it switch?
Usually with heat applied very locally and quickly. The main materials are chalcogenides, things like germanium, antimony, tellurium, GST alloys. They're special glass-like materials.
Okay.
And their big advantage is multi-level storage. They don't just have to be on or off, they can hold intermediate values. This allows for that analog weight modulation like a dimmer switch, which is much more like a biological synapse.
That multi-level ability sounds really key for brain-like computing. Okay, next up, resistive RAM, or RAM. Sounds related but different.
Similar goal, different method.
Yeah.
Our RAM uses resistive switching. You can think of it like tiny conductive filaments, like little wires, forming and breaking inside the material. This changes its electrical resistance.
Elements made of what?
It often involves ions moving around, maybe oxygen vacancies drifting. The materials are typically metal oxides, hafnium oxide, titanium oxide, tantalum oxide are common, also perovskites.
Okay. And I've heard the term memristor connected to this.
Right. Memristors are essentially a type of RRAM. They're really promising for artificial synapses because they can be dense, low power, non-volatile, meaning they hold their state without power, and they enable compute in memory.
Compute in memory, doing calculations right where the data is stored.
Exactly, avoiding that data movement again.
Now, I heard something fascinating about RAM, that sometimes their imperfections can actually be useful. How does that work?
Yeah, that's a really cool aspect. So these devices aren't perfect. There's variability from cycle to cycle or between different devices. They might not switch exactly the same way every time.
Right. Sounds like a problem.
You think so. But you can actually exploit this randomness. It can be useful for things like Bayesian computation, which deals with probabilities, or even mimicking the natural noise in biological systems for tasks like online learning or motion detection. It's like turning a bug into a feature.
Leveraging chaos. I like it. Okay, what about ferroelectric RAM? FerRAM.
FerRAM uses a different property, ferroelectricity. Think of materials with tiny internal electric dipoles, like microscopic compass needles, that can be flipped by an electric field.
So you store data by flipping these dipoles.
Exactly. The direction they point represents a 0 or 1. Common materials are ceramics like PZDT or specially treated hafnium oxide, bismuth ferrite. They offer non-volatility, in-memory learning potential, good endurance, and low-voltage operation, often used in things called FE-FETs or ferroelectric memristors.
Interesting. Then there's MRAM, magnetoresistive RAM. Sounds like magnets are involved here.
Yep, fundamentally different again. MRAM uses magnetic effects. Typically, it involves layers of magnetic material, and the resistance changes depending on whether the magnetic orientations of these layers are aligned or anti-aligned.
Okay.
It relies on effects like magnetic tunneling. Key materials include things like cobalt iron boron, magnesium oxide, nickel iron. MRAM offers non-volatility, it's very fast, and it has this interesting property of potentially offering stochastic synaptic weights that naturally have a bit of randomness, which again can mimic biology.
Stochastic, like the RRAM variability, but maybe more controlled.
Potentially, yeah. It's another way to introduce useful randomness or probability into the system. Think MTJs, magnetic tunnel junctions.
Got it. Okay, moving on. Electrochemical RAM, ECRAM, and ionic devices. These sound very biological.
They really are perhaps the most biologically analogous in some ways. They work by physically moving ions into and out of a material, a process called intercalation.
Like charging a tiny battery, almost?
Sort of, yeah. Materials like lithium cobalt oxide or tungsten oxide are used. The big advantage here is that you can get very continuous, smooth changes in conductance. This allows for gradual synaptic weight updates that closely mimic how our biological synapses adjust their strength. We see them in devices like 3-terminal MEM transistors.
Fascinating. Now this one caught my eye. Organic memristors. What's the organic part mean here?
It means the active materials are carbon-based, organic molecules or polymers, rather than the inorganic oxides or metals we've mostly talked about.
Like plastics?
Yeah, things like polymers like PVP or PDT.PSS, or even graphene quantum dots, and potentially even biomaterials. The switching might involve charge trapping or molecules changing shape.
And the benefit.
The big potential is flexibility. You can make flexible electronics, also potentially lower cost, and maybe even biodegradable or biocompatible devices for implantable systems or direct interfacing with biology.
Wow, flexible, biocompatible neuromorphic chips. That opens up a lot of possibilities. Okay, how about 2D materials? Graphene gets all the headlines, but what else?
Right, beyond graphene, there's a whole family of atomically thin materials, just one or a few atoms thick. Think molybdenum disulfide, hexagonal boron nitride, tungsten diselenide, the transition metal decalcogenides, or TMDs.
And they can act like memristors, too.
Yes, they show various memristive and synaptic behaviors. Because they're so thin, they allow for really novel device designs, potentially ultra-low energy switching, and again, mechanical flexibility.
Yeah.
We're seeing experimental synaptic devices made from stacking these 2D layers called van der Waals heterostructures.
Very cool. Then spintronic devices. How are these different from MRAM, since both use magnetism?
It's a subtle but important distinction. While MRAM mainly uses the magnetic orientation for resistance changes, spintronics tries to actively use the electron spin, its intrinsic quantum angular momentum, in addition to its charge.
Using a quantum property.
Okay. Yeah, employing effects like spin torque to manipulate magnetic states. Materials often overlap with MRAM, like COFEB, Ta, MgO, but also includes multiferroics. People are exploring spin torque memristors, devices based on moving magnetic domain walls, or even exotic things called skyrmions to act as neurons or synapses.
Skyrmions. That sounds very cutting edge.
It definitely is. Still quite research heavy.
Okay, nearly there. Metal insulator transition, or MIT devices.
These exploit a fascinating phenomenon where certain materials can abruptly switch from being an electrical insulator to a conductor, or vice versa, often triggered by voltage or temperature.
Just snaps between states.
Pretty much. Materials like vanadium oxides or niobium oxides do this. This sharp switching is really useful for building artificial neurons, specifically the integrate and fire part. So you see them used for things like Mott neurons.
Makes sense for mimicking a neuron firing. And finally, number 10, photonic neuromorphic devices using light.
Exactly. Instead of just electricity, these use light to represent and process information. They might use materials that change their optical properties, like their refractive index or absorption, in response to light or an electrical signal.
Or material.
Chalcogenides pop up again because their phase change affects light transmission. Also, other phase change materials and silicon nitride, which is common in silicon photonics.
Yeah.
The big draw is speed, potentially processing at the speed of light, and energy efficiency, plus integration with optical communication. Think photonic synapses or optical PCM.
Wow. Okay, so that's an incredible tour of 10 different approaches, 10 sets of materials, all aiming for brain-like computing. It seems like the material science challenges must be immense across the board.
Oh, absolutely. You summarized it well. Each technology has its own specific material needs and its own set of trade-offs.
Yeah.
Do you prioritize speed, energy efficiency, how closely it mimics biology, scalability, cost? There's no single perfect answer.
So researchers are working on improving the established ones, like the oxides for RAM and chalcogenides for PCM.
Right. Refining those, making them more reliable, more scalable, but also pushing hard on the newer platforms, the 2D materials, the organics, the photonics, because they might offer unique advantages down the line. It's a really diverse landscape.
And the biggest hurdle overall is integration and reliability. Getting these novel devices to work reliably, at scale, and play nicely with standard silicon manufacturing.
That's pretty much the heart of it. Integrating these often very different materials and device types with the incredibly mature CMOS platform is a huge engineering challenge. And overcoming those non-idealities, the variability, the endurance limits, while still meeting those incredibly tough performance targets we talked about, that's the grand challenge. It's a massive material science puzzle.
So just to recap, we've journeyed through this really fascinating world of neuromorphic computing, starting with the brain-inspired ideas, the advantages like low power and local learning.
Avoiding that von Neumann bottleneck.
Yeah, exactly. And then diving into this amazing array of hardware technologies trying to make it real, from phase change materials to organics to light-based systems. It's incredible the ingenuity involved.
It really is. And I think a key takeaway is that we probably won't see just one winner emerge. There won't be a single universal neuromorphic solution.
More like different tools for different jobs.
Exactly. We'll likely see a range of specialized hardware. Maybe one type is great for sensory processing, another for learning, another for pattern recognition. Tailored solutions using different materials and devices, optimized for specific tasks. A bit like the brain itself has specialized regions.
That makes sense. So as these systems keep evolving, kind of bridging that gap between biology and silicon, they're not just about making AI smarter in the current sense, are they? It feels like they could fundamentally change computing.
I think that's the ultimate potential, yes. It's a new paradigm.
So here's something to think about. How might you engage with devices that learn and adapt in these much more brain-like ways in the coming years? What possibilities open up when your technology doesn't just follow commands, but genuinely starts to maybe understand and evolve with you, perhaps anticipating what you need before you even ask? Just something to ponder.